All right, hello everyone. My name is James Fiacco, and I'm going to be talking to you about deep neural model inspection and comparison via functional neuron pathways. And if there's one thing that you're going to take away from this talk, I hope it is that it's possible to identify functional components within a neural net that can be associated with external task knowledge. But I would like to keep in mind a caveat that while these associations can be informative for understanding a network, they can't prove there's a causal relationship, and that's kind of true for most probing tasks. So let's start with something simple, and that is neural interpretation can be very complex. And a large amount of that complexity comes from the distance between what an individual neuron does and what the entire network as a whole does. So what we want to do is we want to find groups or patterns of activation within the neurons in a network and group them together in order to create these abstract functional groups that we call neural pathways, because these neurons can be all over the network, but to the extent that they're correlated, they kind of represent a pathway of activation that goes through the network. So during this presentation, I'm going to provide an overview of how to extract and kind of interpret these pathways, and then illustrate that approach on some models for some well-understood NLP tasks to show that these pathways are explainable based on knowledge that we have about that given task. So to begin with the method overview, on the far left, we have the information that's expected to be given before you even try to interpret the model, and that includes the trained model itself, some validation data that you need or that you can run the model on, and then some external task knowledge that's going to serve as the lens from which you can look at your model. And then on the right, you have all the different components of this interpretation method, starting with identifying the pathways, associating those pathways with the external task knowledge that you bring to it, quantifying the pathway effects, which means to find out to what degree you can actually answer questions that you're interested in about your model, and then synthesizing all that information together into some sort of cohesive story. So for the model, our approach is model agnostic, and you don't even have to use the entire model. You can also use a subset of it, and the interpretation approach applies exactly the same. And it starts with just extracting the activations for each neuron from whatever whatever part of the model that you're interested in for each instance in the validation set, running the model for each instance on the validation set. Which gives you a large matrix that has a flattened array of all of the activations for each data instance in your validation set. And with that matrix, you can start trying to actually look for pathways, which we use, which to do, you'd use a dimensionality reduction. In our case, we use PCA because it is simple and is very fast to run, and it also has some other nice properties for this application, where you take your big activation matrix and reduce it down to a smaller matrix that has the PCA factors by all of the data instances. And the loadings, the factor loadings on each one of those factors for each one of the neurons kind of gives you an indication on how important that neuron is for that given pathway, or the PCA factor, which we're calling pathways here. And the resulting value in the dimensionality reduced matrix kind of corresponds to how active that pathway is for that given data instance. So now that we have these pathways, we can start associating them with task knowledge, and we do this through a series of probing tasks. In our case, we specifically use linear probes because they're easier to interpret. And we use them rather than on the neuron level by predicting from activations on the neuron level, we're predicting from activations on pathways. This is an alternative to the paper, which uses a more indirect approach that does actually compare the pathways to neuron-based or like neuron-level probes as well. But the way we're going to talk about it is a little bit simpler. So you start with just the pathway activations from the previous step, apply a logistic regression model, and trying to predict the presence of some sort of external knowledge. This can be parts of speech, surface features, the type of data, or really any other metadata that you have at an instance level. And now we have a choice to make. And that's, what do we actually want to get out of this interpretation? Do we want to know what the model's doing wrong, or do we want to know how this model is predicting something different than another model? This is the choice of interest, and we're going to create a data set, like a custom data set for this, so that we can do another probing task in order to figure out how well our pathway can answer this question. For instance, if you want to know what your model is doing wrong, you just take the predictions of the model and the validation, the labels, like the gold labels for your validation set, and create a new data set based on just the difference between those. Something's similar, you do something very similar if you're comparing two models, where you take the predictions from the two different models and compare them to get your choice of interest data set. Notably, in this case, you do have to do the interpretation approach for both models separately if you want to get interesting information, because it is kind of a directional interpretation approach. And once you have this choice of interest data set, then you can do another linear probe where you predict from the pathway activations the actual the data set that you just created, which gives you a score that represents to like what degree the pathways can actually explain that question that you're asking. And the weights of that probing data, probe, represent the relative contribution of each one of those pathways on that question. So higher weights will indicate that that pathway is important for explaining that question. And now that we have the knowledge activations from the linear probes on the external knowledge, which the weights give you how associated a given neuron or a given pathway is with with that type of knowledge. And we have the functional importance, which is how important or how influential a given pathway is on the question that you're asking about your model. We can start to combine those into an interpretation. By first, we take the weights from the choice of interest probe, and we look for the highest weights that indicate that pathway is important for that question. And then, now that we know that pathway, we can look at the probes for the external knowledge and look at all of the weights for that pathway and all of the different probes and try to find out which piece of external knowledge is best associated with that particular pathway. And what this gives us is it gives us a place to look within the network given by the pathway because there's important neurons for that pathway. And it also gives you what you want to look for, which is represented by what external knowledge that pathway is associated with. And again, there's a caveat where these linear probes are correlational and are really only as good as the external information that you bring to the table. Because if you bring external information that is simply correlated to what the network is doing, you might get a signal even though the network is doing something different. So it's really important to pick your external task knowledge very carefully. So now we can talk about some experiments. And we ran in the paper, we ran our interpretation approach on two models, each for two different tasks, recognizing textual entailment and named entity recognition. For purposes of this talk, we're going to specifically talk about named entity recognition and the two models we used there. We used a CNN BiLSTM CRF from Monhovy 2016, and we used the exact same model again, only we replaced the CNN with a character level BiLSTM. We ran this on the Connell 2003 data set for NER, and the question that we were asking about these models were how do these predictions differ between these two models? So for the performance of the models, these are untuned because the absolute performance doesn't really matter. We're really just interested in the comparison between them. But the CNN-based model did quite a bit better than the BiLSTM-based model. And that's what we're going to kind of take out of this for the rest of the interpretation. So identifying the pathways. In the CNN-based model, we found about 40 pathways that explained about 75% of the variance. And for the BiLSTM-based model, there's about 35 pathways that explained about the same amount. We chose the number of pathways to explain about 75% of the variance because it gave a good balance between the number of pathways that you got and not losing too much information. And the number of pathways is down from the hundreds upon hundreds of individual neurons in each of the models. So now here's some results for a selected number of the external knowledge probes that we used, the very, very limited subset. And we use for the NER test, we use surface features. And as you can see, some of the probes do really well, for instance, title case on both models, and some of the probes do very poorly, like adjectives. And the reason that we selected these, or we displayed these particular surface features is because those were actually the surface features that were most associated with the pathways that were most influential for explaining what these models were doing differently. And you'll notice that title case appears in both of these. What that means is that there's some pathway in the model that some group of neurons that is most associated with the title case of some word. And in both models, how the model is dealing with this pathway is influential in the differences of the predictions between the two models. So this is something that we wanted to dig deeper in. And in fact, there is obviously both of the models were using this pathway to, or had a lot of neurons within this pathway that were dealing with capitalization of letters. I mean, it is title case after all. However, in only the CNN-based model, there was a set of neurons that had nothing to do with title case. In fact, they were looking at these intermediate words like van or der that occurred between names and were almost always lowercase. And what we noticed is those particular neurons were firing to kind of like maintain the state of the named entity in order to prevent it from deciding that the named entity was over when it turned into a lowercase letter. And this was true in the CNN model, but we did not find a similar set of neurons in the BiLSTM model, kind of indicating that this like exception to the general heuristic of like capitalization is important for like proper nouns and named entities might be improving the CNN-based model. So kind of in conclusion, we have with like the neural pathways, we can direct our analysis on specific questions of interest about our model, and then we can use the external knowledge as a lens to be able to figure out kind of what we need to look for in our data or in our error analysis. And then we can identify where in the network we should look for it based on the loadings in the PCA. So that is my talk. Any questions?